Higgs boson,
चंद्रशेखर लिमिट,
string theory,
न्यूट्रिनोस,
quantum entanglement.
कुछ समझा क्या?
Ever felt bored and confused while reading lengthy physics textbooks or articles?
Yeah, on God, bro.
I'm Arnav,
And I'm Pratham.
and welcome to Quark Talk, where we decode all the complexities and simplify these intricate concepts in physics.
They may have seemed too complex to understand until now. So, since this is our first episode and we are named Quark Talk, I felt that we should start by discussing the smallest particles that constitute our universe. And no, I'm not talking about atoms.
Well, let's back up a bit.
Sure. So, like 300 years ago, people thought ammonia and water were elements. Like, how crazy is that?
Yeah, I mean, that is pretty crazy, but yeah, that's what. Scientists weren't convinced with that.
Of course, we wouldn't be here if they weren't.
Yep.
So, this guy called John Dalton comes in and he proposes his atomic theory. And what he basically stated is that all matter is made up of tiny indivisible particles called atoms. So, he believed that the smallest particle that existed in the universe was a spherical shaped particle called an atom.
Well, to break that illusion, J.J. Thomson comes in with cathode ray tubes, and his experiments with cathode ray tubes showed that all atoms contain tiny, negatively charged subatomic particles called electrons. So this went and led to the release of the plum pudding model by Thomson, and it has basically negatively charged electrons embedded within a positively charged soup. But what are those positive charges?
These positively charged particles are called protons. So, Ernest Rutherford, with his famous gold foil experiment, I don't know if you remember, but I studied this in 8th and 9th grade, and I'm sure most of you have done as well. What he did in this gold foil experiment was he fired something called alpha particles into a sheet of gold. Now, that's not really necessary here. What you need to understand is that the deflections that these alpha particles were subjected to proved to us about the existence of a positively charged particle called proton inside the very nucleus of the atom.
So this gold foil experiment showed us that the atom is mostly empty space with a tiny, dense and positively charged nucleus. But why is the nucleus positively charged?
Because the electrons are not within the nucleus as J.J. Thomson's plum pudding model suggested. They actually orbit the nucleus and they are staged in different energy levels, which is later.
We'll get to more of it later.
We'll get to it later.
Yeah, so Rutherford proposed the nuclear model of the atom, which was, as Pratham said, it was it was with energy levels. And why is the nucleus positively charged? Because they're neutrons, these are the third particles within an atom, which are neutrally charged, and this was found by James Chadwick.
So basically they're just AFK inside the nucleus, like they don't do anything?
Yep, the only thing they contribute to is the mass.
God.
And they're the same mass as the proton. So, in the early 1900s, Albert Einstein's theories of special and general relativity and Niels Bohr's model of the atom, these two were the main contributing factors for the groundwork of modern physics. So over the next couple decades or so, the standard model began its formulations, and it was confirmed experimentally between the late 1900s to the early 2000s, where particle accelerators were used to confirm the same. But what is the standard model? Well, the standard model of particle physics is a theory that tells us about the particles that are like the fundamental particles and the interactions. Its development has been very significant in modern physics because it's integrated both theoretical and experimental discoveries over those several decades. But the problem is that it does not account for gravity, dark matter, or dark energy. And this has led to ongoing research in theoretical physics to extend beyond the standard model.
That's interesting.
Yep, so there's still work left to do. And so, to sum it up, Standard Model is the theoretical framework describing all the known elementary particles. And what are these elementary particles? Well, they're made up of two types, fermions and bosons. All fermions have half-integer spin and obey the Fermi-Dirac statistics, named after Enrico Fermi and Paul Dirac. And all bosons have integer spin and obey the Bose-Einstein statistics, named after Satyendranath Bose and Albert Einstein. Bosons have their stuff, but more importantly for today's episode, fermions have two types, quarks and leptons, and their respective antiparticles, which are anti-quarks and anti-leptons. But yeah, so one thing to note is that they're hadrons as well, and we won't get into the details, but not all fermions or bosons are made of quarks, and those that are made of quarks are under the hadron category.
So, like Arnav was saying, there are these particles known as quarks. So that is going to be the main focus of today's episode. Now, these quarks were discovered in 1964, and they were done so with the help of the Large Hadron Collider, which, like all particle accelerators, what it does is that it smashes atoms and subatomic particles together, and it basically allows us to see what the result of this amazing collision is.
And this is one thing we can't do with normal everyday equipment, because it accelerates them to almost the speed of light in some cases.
That's true. And the two physicists who discovered this quark particle are Murray Gell-Mann and George Zweig, and they were working independently on this theory.
So, a quark is an elementary particle and it's a fundamental constituent of matter. Quarks cannot be observed outside of hadrons, and there are 6 types of quarks. So, under a quarks, we get these 6 types, or these flavors, as some like to call it. And they are up quarks, down quarks, strange quarks, charm quarks, bottom quarks, and top quarks.
Those are totally random names, but sure.
Yeah.
Let's continue.
I mean, they sound good at least. So, all the quarks have symbols, which are just the first letter of each type of quark. For example, up as U, down as D, etc., etc. So, antiparticles, which I mentioned earlier, are called antiparticles of quarks, are called antiquarks, and they're denoted by a short line over the symbol for the corresponding quark. So, and as with antimatter in general, antiquarks have the same mass, mean lifetime, and spin as their respective quarks. But the electric charge and other charges have the opposite sign. So, Gell-Mann was, when he was formulating his the name for the quark, because he was the main guy who found it, and he was Zweig and Gell-Mann were both deciding the names independently, and Zweig wanted to call it aces, and Gell-Mann wanted to call it quark. So he initially wanted to call it KWORK.
Quark? Damn.
Yeah, so then he was a little confused of deciding what to do, but then he read James Joyce's 1939 book Finnegan's Wake, and that said 3 quarks for Master Mark. Sure, he hasn't got much of a bark, and sure, any he has, it's all beside the mark. So this was the 3 quarks, because it's very relevant. Yeah. So it's very relevant to the real quarks, and it's the same spelling, because protons and neutrons are made up of 3 valence quarks. We won't say that right now. We'll give it a minute or two. But valence quarks, we'll leave that aside for now. So that's how he got the name quarks. And it was, why not aces, you say? Because Gell-Mann's quark theory was highly famous, more famous than Zweig. So
he just had a way with the naming system. He had that sort of charisma that maybe Zweig didn't have. So yeah.
So now protons, we normally say protons and neutrons are made up of 3 quarks. Well, that's a white lie. Because that's a big simplification. The 3 quarks mentioned are valence quarks, and there can be many more quarks in them, but the catch comes where each of those quarks will have its own anti-quark, which will
basically cancel
out. Yeah. So it will sooner or later cancel out, and all the time new quarks and anti-quark pairs are forming and being destroyed, and everything is happening, and we can't really tell an exact number of quarks that are there.
So it's not measurable, is what you're saying.
Correct.
Yeah, okay.
But we can tell the valence quarks because the charges cancel out. But what are the electric charges of quarks? So quarks have fractional electric charge values. It can only be negative 1 by 3 or positive 2 by 3 times the elementary charge E, and E is negative 1.69 into 10 raised to minus 19 coulombs. And this depends on the flavor, if it's negative 1 by 3 or positive 2 by 3. So it's very simple to know. Up, charm, and top. So they're similar, positive words you can say.
Yeah.
So positive words, they are collectively referred to as up type quarks, and they all have the positive charge. So that's pretty simple. So positive, positive, positive. So that's positive 2 by 3. And the other three, which are down stage and bottom, which are down type quarks, obviously, have a charge of negative 1 by 3. And that's sums it up about the charge. But you have to keep in mind that for hadrons, the electric charge is the sum of charges for all constituent quarks. So basically, you have to do some maths, and the maths has to be an integer.
So wait, if the charge on a proton is +1, if I take, say, 2 up quarks and a down quark, that'll give me...
So that's going to be 2 by 3 plus 2 by 3, negative 1 plus negative 1 by 3. So
it'll basically amount to 1. So is that the combination of the valence quarks inside a proton?
Yes. So similarly, for the neutron, we have 2 down quarks, which is going to add up to negative 2 by 3, and 1 up quark, which is going to be positive 2 by 3, which effectively cancels out to 0. And that's why a neutron is neutrally charged.
That's interesting.
Yeah. So moving on to spin. Spin is an intrinsic property of all elementary particles. And as said earlier, because quarks are fermions, and all fermions have half integer charge, quarks have the same. So quarks also have this other property called color charge, and it's not like the color we see day to day, but it's according to quantum chromodynamics.
That's a big word.
Yeah, but don't get scared. It's basically just saying that quarks possess that property of color charge, and there are 3 types of color charge. And they're labeled blue, green, and red. Don't get confused with the visible light part. That's slightly different at least. So each of them is complemented by an anti-color. Well, you don't have that in day-to-day life. So have you ever heard of anti-blue, anti-green, and anti-red?
No.
So every quark has its color, and every anti-quark has its anti-color.
Okay.
So that quantum chromodynamics is a study of strong interaction between quarks and gluons. And quarks are mediated by gluons, and gluons are something for another episode. And quarks have some... What do you want to say about mass? So they have, I think...
So basically the sum of these 3 quarks inside, the valence quarks inside a proton, is 1/50th of the total mass of a proton. So that just tells you the amazing scale, how small these quarks are, and how advanced we have come to that we can
make these precise measurements and calculations. So the mass of a quark varies between the type of the quark. It can range from 5 to 17,500 MeVs. And this so quarks, why we chose this topic is not because we felt interested that no one has or ever will see a quark in isolation, because quarks are always found in pairs, and the more energy you put in separating the pair, the stronger is the mutual force of attraction. The moment you reach that point where it's about to be separated, each quark creates another quark because of that immense energy. And similarly explained by the E is equal to mc squared equation. So now you started out with one pair, and now you got 2 pairs of quarks.
Yeah. So when it comes to the point that these quarks are separated, they form 2 sets of quarks, because the tremendous amount of energy that you are trying to put in to basically pull apart to separate these quarks, it is being used as stated by the mass energy relation proposed by Einstein. It is being used to convert it into mass, basically. Yeah. So that's why you have the creation of these 2 new quarks out of nowhere.
Yep. And because E is equal to mc square, as said before, it takes a lot of energy to make a little amount of mass, or a little amount of mass to make a lot of energy. So that's fine, but what are the real life applications of quarks? Why do we need to know about them?
That's very interesting, because there's the application of quarks like a basic application is in nuclear fusion, where these light atomic nuclei like hydrogen,
And helium.
yeah, they actually fuse. So they both of them combine against positive repulsive charges and
Of the nucleus, yeah.
and they release a tremendous amount of energy.
And that is the fuel for most stars, or like, I mean, all stars in the universe. And that is, and one of those stars is the sun. And that provides the essential heat and light which is necessary for planet Earth to survive, like the inhabitants.
But you might say, like, what role do quarks play here? So, what quarks do is that they are held together by this strong nuclear force, and it is mediated by these particles called gluons. And this force is so incredibly powerful, and it is much stronger than the electromagnetic force that repels the positively charged protons of the two nuclei that are fusing. So when they fuse, this strong nuclear force overcomes this repulsion between those two protons.
So basically, this effectively allows for nuclear fusion to happen. Otherwise,
Yeah.
it would have been stopped and we wouldn't have
And
been alive.
yeah, because we wouldn't get any entropy from the sun. Well, that is
Another topic for another day.
But
So this fusion process, it does release a tremendous amount of energy, and that energy is required for life on Earth, and it is a result of the same E is equal to mc square equation by Einstein. And because the mass of the resulting helium nucleus is slightly less than the total mass of the original hydrogen nuclei. So when you convert helium to hydrogen, which is a lighter element, to a heavier element, you get slightly
some mass is basically missing.
Yeah.
And that mass is released as energy, as stated by...
that's a missing mass.
Yeah, correct. And we have not just got the idea of this episode from the name of our show, which is Quark Talk, but
We've been interested in it, yeah.
Yeah, we actually want you guys to understand what the whole funda of the quark is all about. So, it is not just an elementary or a fundamental particle, but it is one of the building blocks of the universe, and without it, our world would basically be incomplete.